Hello, honors physics students. Okay, so we're deep into our study of charges and electric fields and things like that, and all this is very abstract. It's very difficult to imagine these tiny, tiny objects. We're trying to visualize how big they were. That's really difficult, and they're moving really fast. We're not used to such speeds, and this idea of electric field is also very abstract. So a lot of this is very difficult to visualize, and so I always like to try to introduce as many analogies as possible. So let me help you out here with an analogy. Let's say for our next big physics party, hopefully some restrictions are lifted, we're able to get together, but we still want to socially distance ourselves from each other. So we decide to go outside and enjoy nature. We go on a hike. All right, so we get a map of a local mountain range. We pick a mountain that's maybe not too steep and not too tall because, maybe we're physics students, maybe we're a little out of shape from all our social distancing, all our quarantine activities. And so, maybe we can't scale a huge mountain, but we decide to scale this mountain, right? So we get the height of the mountain, and being physics students, we want to plan everything out, right? So we start doing some calculations to figure out how much time it's going to take to get up the mountain, and how much energy we're going to spend getting up the mountain, and how many calories we're going to burn. And we decide to pack a cooler full of food that we're going to stock full of all the food necessary to replace all those calories we're going to burn by going up the mountain, right? So we've dragged this cooler food up to the top of the mountain, and of course in doing so, it's going to take a lot of work, right? It took a lot of work to get that cooler food to the top of the mountain, or it would take a lot of work to get it up there, right? All right, so we plan it all out, because that's what we do, and the day of the hike comes, and it is pouring rain. And we say, no amount of exercise is worth this. So we decide to cancel the hike. We don't take the cooler food to the top of the mountain, all right, because we just cancel our plans. All right, so a couple of questions. If we had decided to, even in the rain, take the cooler food to the top of the mountain, it would have taken a lot of work, right? But work becomes energy. What sort of energy would the cooler food have? Well, of course, it would have lots of gravitational potential energy. Our work became the gravitational potential energy of the cooler food. Okay, that's good. But we did decide to cancel the hike, so we didn't do that, right? Second question. In canceling the hike, does the mountain disappear? Of course not. It doesn't make any sense. Okay, so keep all this in mind as we introduce a new term, called electric potential. I put electric in parentheses because really it's usually just called potential, but is really electric potential. Okay. So what is this new potential, this term called potential? Well, first of all, it's not potential energy. That's the first confusing thing. Potential energy are different things. Let me explain. Potential, in the analogy I just talked about, is the elevation. So this is analogous to the elevation, the height of the mountain. Okay, so whatever potential is, you want to think about that mountain, think about how tall it is. That's the potential. Okay, and remember, in taking that cooler food to the top of the mountain, we did a lot of work, and we gave the cooler food a lot of gravitational potential energy. Even if we didn't actually take the hike, the mountain is still there, representing a possibility of that cooler food having potential energy. So this idea of potential is like the possibility of having potential energy. So potential is the potential to have potential energy. I know, that's horrible. That's horrible. I really wish we had another name for it, but we don't. We're going to still call it potential. That's the name for it. And then to make matters worse, the symbol for electric potential is a capital V. I know. And make it even worse, it's actually a capital V with little lines on top. You notice that there's little lines here on top of the V, and I want you to put those little lines right there on the end there. So it's not just capital V, it's capital V with little lines. You don't have to say with little lines every time, but just know every time you write the capital V, it has to have little lines on top. That's the symbol for electric potential. So none of this makes any sense. I get it. But this is a very convenient way of picturing what's going on here. It's another way of visualizing it. Okay. Now, when you go up and down the mountain, you don't really care about really how tall the mountain is. You care about how much you went up the mountain and how much you came down the mountain. So you care about your changes in elevation. So we're going to care about a change in potential, a delta V, which we'll define as the change in electric potential energy per charge. We're going to go ahead and box it in. And notice for the first time, no absolute value signs around the charge, which means that the sign of the charge will matter in this case. Now, we already know that the change in electric potential energy is related to the work done by the field. We had that little equation that the work done by the field is the negative change. And since this is just change of potential energy, we can say that's the negative work done by the field per charge. We're going to box this in as our alternate equation for electric potential difference, as it's called. All right, let's do our usual stuff, vector and scalar, right? So the top of each of the equations is either energy or work, which we know, of course, is scalar. The bottom is charge. Is that vector or scalar? Remember, it is scalar. There's no directionality. Yes, I know we have positive and negative charges, but that's not telling anything about a direction. It's just an amount of something something has, so it's just a scalar. Right? So yes, potential will be a scalar as well. For the units, well, the top is in joules, because it's either work or energy. The bottom is charge, so it's in coulombs. So, of course, our units are joules per coulomb. Nothing fancy about that. Although we do rename the joule per coulomb after Alessandro Volta. This is a volt. another capital V, but this time it doesn't have the lines on top. I know sometimes it prints here with the lines. Don't do that. Just a regular capital V. So there's a capital V with the lines on top telling you the quantity of potential. The unit is just the capital V named after Mr. Volta, so it's called a volt, and 1 volt is 1 joule per coulomb. Now this can get a little confusing if you're not careful with how you write it. You may write something like this, or see something written, delta V equals 10V. Notice this is the V with the lines on top. This is the V, pretend it doesn't have lines on top at all. Right? And if you're not careful, with this one having the lines and this one doesn't, you might divide both sides by V and prove delta equals 10, which has no mathematical meaning whatsoever. So just be really, really careful. Whenever you write the delta, the V for potential, it's got the lines on top. The V for the volt does not. Okay, let's define our terms here. So delta V is potential difference created by some other charge. Now, I know you don't really know what potential is just yet, but just be aware charges can create potential, and in this equation, it's created by something else. And even though you're still not quite sure what potential is, every time you see potential, you see the V, you see the delta V, you're thinking of the mountain. It's like the height of the mountain. The Q in the equation is the lowercase q, which is sort of like the test charge, but I want to refer back to the same way we've been using it as the moving charge. It's the thing moving around. In fact, in our analogy, it's the cooler of food. It's the thing we moved up and down the mountain through a height difference. So the charge moves through a potential difference. And this is not the one creating the potential. That'll make more sense soon. Okay, so let's look at our easy example. Let's look at our oppositely charged parallel plate. So go ahead and draw that here. Positive on top, negative bottom. There's nothing magical about that, but just helps us visualize what's happening. We have our electric field lines evenly spaced, parallel to each other, pointing from positive to negative. Our uniform electric field. Keep it nice and simple. Let's put a positive charge there. This is like our cooler of food, right? And if we move the positive charge towards the positive plate, we're putting it where it doesn't want to go, which means it took a lot of work to get it there, which means we're giving it electric potential energy, right? But we're also moving it this way. So this is our cooler of food. We're moving the cooler of food where it doesn't want to go. Is that up or down the mountain? That's up the mountain, right? That means that over here must be the high elevation, like the top of the mountain. And so we're going to say that positive charges, like the positively charged plate here, creates a region of high potential. So the positive plate here is representing the top of the mountain, a high elevation, a high potential. That means what's over here? Well, this is where the cooler started, at the bottom of the mountain. So that must be the negative plate. So that must be the region of low potential. So negative charges, like this negative plate, creates a region of low potential. So this is like the high elevation, this is like the low elevation. Here's our cooler of food, top of the mountain, bottom of the mountain. Elevation is like this new concept of potential. That's what we're trying to visualize here. Okay, so here's our mountain, here's our cooler of food. That's represented by the positive charge, and here's our plates, right? So just really put them side by side so we can see this, right? So here's the top of the mountain. That's where the positive charge doesn't want to go. That means that's the region of high elevation. That's the region of high potential. Here's where the cooler food started down here, the low elevation. That's where the positive charge sort of wants to be. That's at the low potential, right? So positive charges create regions of high potential. It's like they raise up the landscape. Negative charges create a region of low potential. It's either the bottom of the mountain or maybe even like a pit or a valley, something even lower than like sea level, where sea level would be like a zero, sort of arbitrary position of zero. Put a positive charge there, that's the thing moving around. That's the cooler of food. The cooler of food moves up or down the mountain. The positive charge is the thing moving around between the plates. So the plates create the potential difference, just like the mountain creates this height difference. The cooler food moves around in that region, the positive charge moves around in that region. It's the thing experiencing the difference in potential. So the plates create the potential, the charge experiences it. The mountain creates the elevation change, the cooler experiences it moving up or down. So that's the analogy we're making. Okay, so let's go back here. Now let's say we take our positive charge and we let it go. Where would it naturally want to go? Well, it naturally wants to, of course, go to the negative plate, right? It's going to follow the field lines, it's going to attract to the negative plate, and in doing so, is it gaining or losing potential? Well, it started at the high potential, it went to the lower potential, it's clearly losing potential, right? That's like our cooler of food, we bring it to the top of the mountain, uh-oh, we let go of it, where's it going to go? It's going to roll down the mountain. It's losing elevation. Elevation is like potential, and so positive charges, like the cooler of food, if you let go of them, they tend to lose potential. They tend to go down the mountain. That makes sense, okay? But what if it's a negative charge? If I put a negative charge there between the plates and let it go, where's it naturally going to go? Well, it's going to go to the positive plate. Well, right? That means it's gaining potential because the charge here has nothing to do with the plates. The plates still create a high potential here, a low potential here. And if it started in the middle and it went towards the positive, it's going to a higher potential. So this negative moving charge tends to gain potential. That's a little bit weird. That's like taking our cooler food, letting it go at the bottom of the mountain. It shoots up the mountain. The cooler food is not going to naturally do that, right? So here's where the analogy sort of fails. Although a couple of years ago, a student said, ooh, Mr. Sadowski, replace the cooler food with a helium balloon. Because you take a helium balloon and you let it go at the bottom of the mountain, where does it go? It rises, it gains elevation, okay? So in our analogy, negative charges were represented by helium balloons. They like to go up the mountain. Negative charges tend to gain potential. They go up to the top of the mountain. Positive charges tend to lose potential. They tend to go to the bottom of the mountain.